All right. Thank you all for being here today. Today we have Mar with us. She's originally from Lanzarote and she did her bachelor's and her master's at the Universitat de Barcelona. In 2021, she got an FBI fellowship to begin her PhD at the ICCUB. And she focuses on massive stars, binaries, high energy astrophysics. She is part of the Magic Collaboration and also the Diversity, Inclusion, and Equity Commission at the ICCUB. We're very excited to have her here today, so take it away.
Thank you. Thank you for the opportunity to present my work here. Today I'm going to talk about our project that is both a search for runaway stars, stellar bosons, and binaries in high energies. So, wait. Our project have three key points: massive stars, bosons, and gamma ray binaries. And today we will see that there is a key ingredient that unites all them that are runaway stars. For this project, we work with a lot of multi-wavelength data from radio to gamma rays, and of course, using data from the Gaia satellite. But let's start from the very beginning. Massive stars are massive stars with masses greater than 8 solar masses. They have high luminosities and strong stellar winds. They are mostly in closed binary systems, so they are interacting with companion stars during their lifetime, and this results in the production of interesting and exotic binary products. Here we have some examples of these post-interaction products. So we see that the binary future in massive stars provides a rich set of astrophysical objects with different physical phenomena. On the other hand, runaway stars are stars with a high peculiar velocity with respect to the environment. And there are several works in the literature about runaway stars that found significant fraction of Hola, ¿sí? That found significant fraction of massive O and B type stars as runaways. However, we see that there is a significant scatter in the results because for O-type stars, we have runaway percentages from 20 to 50%, and for B-type stars, we have a runaway percentage around 5 to 10%. Why do we have all this difference? Well, because there is a diversity in the input data and the method to detect the runaways. We have works using IPARCOS data, early releases of Gaia data, and also different methods working with proper motions, 2D or 3D radial velocities, the distance of the galactic plane, and also some work with a specific runaway threshold. So we need a new work using the last release of the Gaia data and also working with a method to detect runaways that is more homogeneous. On the other hand, we have that O and B runaway stars, O and B stars are hot and massive, and they have a fast evolution, yielding large amounts of their mass through strong stellar winds. While O and B type stars, they are fast rotating stars with circumstellar disk that show emission lines. As for the binary properties of each type of stars, we have that OB stars are mostly in binary systems, with a higher percentage for the O-type stars. While for the O and B type stars, the binary characteristic is less constraint, but we have that the companions are usually sleep stars or more interesting for us, binaries with compact objects. And this leads to our connection between the world of the massive star and the world of the gamma ray astrophysics, because massive stars can result in exotic interaction products that are high energy binaries. And this is our systems such as X-ray binaries, and gamma ray binaries. So they have large names, but they can describe in a few words. These systems are just a massive star with a compact object. And this compact object can be a neutron star or black hole. That's all we need to have X-ray or gamma ray binaries. Observationally, we have that high mass X-ray binaries have the maximum of the non-thermal emission at X-rays, while gamma ray binaries have it at gamma rays. So it's quite intuitive to remember. From these two systems, we have, well, as the name says, gamma ray binaries emit at gamma rays, but we also have some high mass X-ray binaries that emit also at gamma rays. So if we focus on these systems and the binary systems that are gamma ray emitters, we have two main scenarios to explain the self-emission. One is the microquasar scenario, where we have an accreting compact objects that launches jets, and in these jets is where the gamma ray emission is produced. While the other scenario can be the pulsar wind binary, where we have a pulsar as non-accreting pulsar, and then the gamma ray emission is produced in the collision between the stellar wind and the relativistic wind of the pulsar. Focusing in the gamma ray binaries, we have that there are only 9 gamma ray binaries that are known. 3 of them have a confirmed pulsar as compact object, and they also have very different orbital configurations with different periods and eccentricities. This is the table with all the gamma ray binaries that are known. And we see that something important is that the companion stars are always of O and B type. The orbital periods are quite different among them, and we have that they are typically located at a few kiloparsecs, except for the one that is in the Large Magellanic Cloud. So we have just a few sources, and then we have a lot of open questions. For example, does this population is representative of the real gamma ray binary population? Do all of them contain pulsars? Why they only have companions as O or B type stars? So, well, we have a lot of main open questions. This is a list of some of them, but we want to try to answer them, and that's why we want to find new gamma ray binaries. On the other hand, we have that from the non-gamma ray binaries, some have high to extremely high peculiar velocities. The most important part for us is that 3 out of the 4 gamma ray binaries with available space velocities are runaway systems. So here we find the connection between the runaway stars and the gamma ray binaries. Why do we have so many runaway gamma ray binaries? Well, there are 2 main scenarios to explain the runaway origin. One is the binary supernova ejection scenario, where the runaway velocity is acquired as a consequence of a supernova explosion of the most evolved star in a binary system. And the other is the dynamical ejection scenario. In this case, the runaway velocity is acquired after the interaction of the 3 or more body interaction in the core of a dense cluster. These 2 scenarios produces both isolated runaway stars or runaway binaries. And from these 2, this one especially produces runaway OB binaries with compact objects that are the ones that we are interested in. So we focus now in this scenario. So imagine that we have a binary system with 2 massive stars, and they are orbiting around the center of mass. At some point, the most evolved star evolves faster and explodes into a supernova. Then we will have that the system will remain bound if less than half of the mass is lost. So as a consequence of this supernova explosion, we will have that the supernova ejecta is moving in the opposite direction of the binary system. And this effect is known as the kick, and this kick induces a runaway velocity to the system and changes the orbit. So after all this scenario, we can end up having a binary system that is now runaway and have a compact object that could be a runaway gamma ray binary. So to recap, we have that massive stars of OB type are a significant fraction of these massive stars are runaways. We also have that massive stars are in binary systems. So if we take all these ingredients, we may find gamma ray binaries that are runaways. This is our project, the search for gamma ray binaries through massive runaway stars. And at this point, we have done this first step, that is the search for runaway stars among O and B type stars. This was published in a paper last November. And now we are in this second step, that is the search for the gamma ray binaries. And for this, we need to look for binary hints. Hola, ¿sí? Vale. The blue point is the part of the work that we have already done or published. And these 2 points that are in gray are that is ongoing work. So I will focus now in the results of this first paper. That is the search for runaway stars. Well, we have that the gamma ray binaries have as stellar companions O and B type massive stars. So we need catalogs of this type of stars, and for this we work with the GOSC catalog, that is a catalog of galactic O-type stars, and we also work with the BeSS database, that is a catalog with B-type stars. We cross-match all of them with Gaia DR3, and we apply some quality cuts. And after that, we end up with a catalog that we call the GOSC Gaia DR3 catalog that contains 417 stars, and the BeSS Gaia DR3 catalog that contains 1,335. These are, well, from now on, we will have that the stars of the GOSC Gaia DR3 catalog are in blue, while the stars of the BeSS Gaia DR3 catalog are in red. This is the projection in galactic coordinates of all the stars in our sample. So here we have the position of the galactic center, and we can see that most of the stars are located at the galactic plane with some dispersion. And we also see that the sample is not homogeneous because there are dedicated surveys in specific areas. And also we see that there is quite more dispersion for the B-type stars than for the O-type stars. At the magnitude, this plot here, our sample stars at magnitude 6, Gaia magnitude, because we filter our catalog for Gaia magnitude less than 6, because this was a quality cut. And the O-type stars go from magnitudes of 6 up to 15, while the B-type stars goes up to 17 Gaia magnitude. This other plot here corresponds to the distances of the stars from the sun. And we have that our sample can reach distances of mostly 9 kiloparsecs, but we have a broad maximum around 2 kiloparsecs. And finally, the galactocentric coordinates in X and Y. Here, this yellow point here is the sun. And we have that there is an absence of O-type stars around the solar neighborhood. This is
because when we filter in Gaia magnitude less than 6, we are also filtering the brighter and the closest stars. This effect is not seen for the B-type stars because the density is much higher. And before proceeding, I want to comment that here we use this correction for the Gaia DR3 parallaxes because Gaia DR3 parallaxes were uncertainties were underestimated, especially for the bright stars. So we use the correction of Maiza Payanis 2022, both for the parallax uncertainties and the parallax 0 point. So let's say that we went from the Gaia DR3 parallaxes to our own distances using this reference. So now that we have all our catalog of stars, we have to find the runaways. And for this, we need first to compute velocities and then to define a runaway criterion. For the velocities, we use a two-dimensional velocity system that is composed of a tangential velocity to the plane of the sky, to the galactic plane, a parallel to the galactic plane, and a second velocity component that is perpendicular to this plane. And we only use this two-dimensional velocity system because Gaia does not have a lot of radial velocities for this type of stars. Let me just do one slide about technical details in these references, about these reference systems. This is the figure with all the reference systems that we use. Here, the galactic center, this is the sun, and imagine that this is a star that we want to compute its velocity. So these X and Y coordinates are the galactocentric coordinates. To compute velocities, we need positions, parallaxes, and proper motions, and radial velocities, but we don't have radial velocities. So we need to assume a galactic rotation curve and compute a theoretical radial velocity. After that, we have to do the user transformations from the local standard of rest system that is here in blue and the regional standard of rest system that is that on green. And we end up defining a new reference system, rotating the previous one, that is this one in red. And this reference system is composed of this tangential velocity that is parallel to the galactic plane, the line of sight velocity that is in the line of sight, and the perpendicular velocity to this plane. So why we define this new reference system? Because in this way we can the theoretical radial velocity mainly affects the line of sight component. So we can just work with this two-dimensional velocity system that will be more reliable. Once we have the velocities, we define the runaway criterion. We consider a runaway star as that with a high 2D peculiar velocity at a 3 sigma confidence level. These are the histograms of the velocity components for each sample. Remember that the O types are in blue while the B types are in red. And we compute the histograms. This top panel are the histograms for the tangential velocity component, and these other panels are the perpendicular velocity component. So we compute the histograms with a binning of 2 kilometers per second and apply Gaussian fits to them. Well, I see now that it is a bit small, but the standard deviations are always of 7 for O-type stars and around 9 for the B-type stars, while in the perpendicular component, we have standard deviations around 5 kilometers per second for both the O and the B-type stars. So looking at these histograms, we see that most of the stars are around 0, 0 velocities with some dispersion, but there are other stars that are affecting this Gaussian fit. So we decided to apply a 3 sigma clipping that improved the fits, and we just now obtain new and smaller standard deviations, around 6 and well, still 9 for the B-type stars, and a bit lower than 5 in some cases. So now we use this runaway criterion to find the runaways. We define this E parameter that uses both the velocity distribution and the individual errors of each star. And basically, we classify as runaways all the stars that have a E parameter greater than 1. That means the stars that have a significant 2D velocity at a 3 sigma confidence level. So in this way, our method is not depending on a specific runaway threshold, but on a significant velocity at a 3 sigma confidence level. These are our results. These are 2D velocity plots. The x-axis is the parallel velocity, the tangential velocity, and the y-axis is the perpendicular velocity to these planes. Now we have the stars that we don't classify as runaways are in black, while the stars that are in colors are the runaway stars. For the O-type, again, we have the blue ones are the O-type stars, and the red ones here and are for the B-type stars. And these are the runaways in red and the runaways in blue. Taking into account that these plots are in different axis scales. So clearly we can see that the O-type stars are usually with higher runaway velocities than the B-type stars. For the GOSC Gaia DR3 catalog, we found 106 stars. That is 25.4% of the catalog. And the 2D peculiar velocities are up to 200 kilometers per second. While for the B-type stars, best Gaia DR3 catalog, we found 69 runaway stars. That is only 5.2% of the catalog, and their velocities, 2D velocities, are a bit lower. For this sample, we found 42 new runaway stars, and for the B-type stars, we found 47 of new runaways. So the majority of this sample were new runaways discoveries. This source here is a gamma ray binary, a runaway gamma ray binary, one of the previous ones that I mentioned. So we were able to recover a known gamma ray binary with our method. And another relevant fact for us is that the runaway velocities of these sources are compatible with the runaway velocities of the non-gamma ray binaries. We also compute simulations, 3D simulations. We simulate a radial velocity that will include to this method. And then if we have another velocity component, we can find more runaway stars. That's why we have here like some runaway stars in the region of the field stars, because now we are including this other component. Previous work suggests that the runaway percentages could be 2 or 2.5 higher if we include a radial velocity. And with our simulations, we found factors of 1.2 or 1.3 for the O or the B-type stars that will translate into a runaway percentage of 30% for the O-type catalog and 6.7% for the B-type star catalog. We also compute a similar study, but for spectral type beams. We did these divisions to have a similar statistic between each beam, and we found that the runaway percentage decreases as we move to later spectral types. This was also, well, if we look at the literature, we have some works that claim that the binary supernova scenario will result in a slower ejection of less massive stars, while the DES scenario will result in faster ejection of more massive stars. And this is indeed what we see here. We have the most massive stars with higher velocities and the less massive with slower velocity. So maybe our O-type stars are mainly produced by the DES scenario, while the B-type stars could be mainly produced by the BSS scenario. Dorigo-Jones 2020 found that the percentage between one scenario and the other was 2 or 3 times higher for the DES. And we found a difference in runaway percentages of 5 between the O and the B-type runaways. So this could mean that we are that this reinforced the dominance of the DES scenario versus the binary supernova scenario. Comparing to previous works, we found similar percentages than in previous works, but we want to point out that our method is not dependent on a specific runaway threshold, so it is more homogeneous in this sense. These are again the galactic spatial distributions, but now we have the distinction between the field stars and the runaway stars. So we know that runaway stars have been expelled from their birthplace because of as a result of the runaway formation. And this is exactly what we see when we look at the galactic longitude, because we found that for O-type stars, the dispersion is 2 times higher for the runaways than for the field stars. And for the B-type stars, the dispersion is 3 times higher for the runaway stars than for the field stars. So we did all this work for the runaway stars. They are very interesting, but we were interested in actually finding new high energy binary systems. So we cross-matched our samples of runaways with the high mass X-ray binaries catalog of 2023, and we found 5 high mass X-ray binaries. I mean, all these were already known. And for the O-type stars, we have also 2 high mass X-ray binaries for the B-type stars. And with this work, we classify these 2 high mass X-ray binaries as runaways for the first time. As for the gamma ray binaries, we had that 3 non-gamma ray binaries are runaways. The first one, this LS5039, we were able to recover this gamma ray binary as runaway in our method. The second one, 1259, was not classified as runaway in our method, but this was somehow expected because this source is runaway mainly in the radial direction, that is where we are blind. So maybe taking radial velocities, we should be able to detect it as runaway. And finally, this other gamma ray binary, 1018, this was not contained in our input catalog, so well, it is not in our sample. So now I will show some preliminary results, because to unveil the possible nature of the possible gamma ray sources, we need to look into multi-wavelength data, because in particular, gamma ray binaries have non-thermal emission in radio, X-rays, and gamma rays. So we started by looking into these wavelengths. For radio, we cross-match with this list of radio catalogs here. In X-rays, we cross-match with the catalog of high mass X-ray binaries of 14, and we also use the Chandra source point catalog of 2.1. And finally, we cross-match with the last release of the Fermi collaboration, that is the Forest-Gaia DR3. There are some counterparts. There are just a few counterparts, but we should take this as a lower limit and preliminary results. And a lower limit because not all our runaways have been observed. So, and also, I have these two sources here, because Fermi is high energy gamma rays, but our gamma ray binaries are also detected in very high energy gamma rays. And we really don't know how is this population of gamma ray binaries. So this population that we are looking for could be faint at high energy gamma rays, at Fermi energies, but we may be able to detect it at very high energy gamma rays. So it's basically non-trivial to find these sources. Another part of the work, not related to the binaries, but related to, well, it could be some stellar bosons in binaries, but we'll especially look for stellar bosons around our runaway stars. So this was mostly done in the infrared. Stellar bosons. A boson is formed by the accumulation of interstellar matter as a runaway star sweeps and hits the interstellar medium. This gas and dust that is behind the runaway, in front of the runaway, mostly emit at infrared wavelengths. And we also have that if the velocity of the runaway star is supersonic with respect to the interstellar medium, a strong boson can take place, and this means that we can have particle acceleration up to relativistic velocities. So this system could end up emitting at radio and not thermal radio emission, X-rays, and also possibly gamma rays. And another thing is that if we have the boson face on, we may see this boson in infrared as a spherical bubble. And finally, these boson studies are relevant to constrain ESM densities, particle acceleration, and try to look for non-thermal emission in these sources. So as I mentioned that the heated ambient gas and dust mostly emit at infrared wavelength, we search for WISE data, And this emission is mostly expected at WISE band 4, that is 22 micrometers. So we expected WISE for images to try to look for these boson or bubble-like candidates. And we also need to correct the Gaia DR3 proper motions because of the ESM motion caused by galactic rotation. So with these 2 points, we define a criterion to detecting bosons or bubbles. I mentioned also bubbles because when we inspected the images, we end up finding different infrared structures, and some of them were bubbles. So our criterion was based on 2 things. First, that we have something that reminds us to a kind of boson or bubble-like structure around the runaway stars. And second, that this arc-shaped structure or the rim of the bubble is in the actual direction of the correct motion of the runaway star. These are preliminary results. As I mentioned, when you expect WISE images, you can find different structures. So we basically define 3 categories. One is the category of the new bosons or bubble-like candidates. The other is the category of non-boson or bubbles, because we also found some non-bosons among our runaways. And we have a miscellaneous category that is basically whatever infrared emission that we found around the runaway stars. We found 60 sources, but most of them were just B stars with some nearly point source emission that could be because of the circumstellar disk. For the new bosons, we found 13 in total, well, 9 boson candidates, 3 bubble-like candidates, and 1 mixed structure. That this, we call this to something that is between a bubble or a boson, because it is not always easy to clearly define what it is there. And comparing to the literature, we found that 69 bosons were already known in our sample. Again, these are preliminary results. These are the RGB images in these WISE bands. And here I show some examples of what we found among our runaways. These arrows are the direction of the Gaia DR3 proper motion, the one that is dust and white. And the other one, the one that is in cyan color, is the correct proper motion. So we basically look into this direction when we want to find a boson or a bubble. And these 2 arrows are of 2 amino size. So yeah, this is one example of a boson. This is also a kind of boson, and this we classify this one as a kind of bubble. For the category of the non-sources, we also have found bosons. And this, I wanted to show this one to explain what we call to a mixed structure, because this could be a kind of bubble, but we also see some kind of curvature in the direction of the motion, of the correct proper motion. So we call these mixed structures. And finally, the miscellaneous category that, well, you see that we found here different infrared structure that we really don't know what it is this, we designate a category that we call mini bubble, because this was similar to a bubble, but it was only 2 times the wise being in W4. So and this was mostly in the B-type stars. So we call these sources mini bubbles. This here is a kind of bubble in the direction of the motion, but also this one here, but they are, let's say that they are low confidence bubbles, and we also have some weird things in the field. So we left these sources as a miscellaneous category that could be also interesting for other studies. Once we have these bosons, we geometrically characterize these bosons in infrared. That means that we measure we measure some geometrical measurements, that is the R distance, that is this one that goes from the runaway star to the maximum of the emission on the boson. We also measure the length of the boson in an arc-shaped structure, and we measure the width of the bosons. This table here shows the mean values of these distances, and these are all projected distances in the plane of the sky. We have both the mean values in arc seconds and in parsecs, and to go from one to another, we use the distances that we compute from Gaia. And we can see that more or less the standoff distance and the width are always at around less than 1 parsec, while the length of the bosons are usually twice these values. As I mentioned, boson studies can be used to find interstellar densities, and we use this equation to derive interstellar density of the median and the position of the bosons. And for this, we use our geometrical characterization and also stellar wind velocities and mass loss rates from the literature. In this case, we use the reference of Pink 2021. So we found densities of around 1 to 10 per cubic centimeter, but there were also some very high values up to 150. So we guess that these highest values could be are always associated to small standoff distances, and this could be attributed to the projection effect that will lead to overestimated ESM densities. And finally, I want to point out that these estimates will be just used as estimates, because we have quite a lot of stellar uncertainties in the mass loss rates, the stellar wind velocities, also the geometrical characterization. So this should be used with caution. Now, if we look, we also look for radio emission of these bosons. And for this, we also we look in these catalogs here, and what we found was that 2 bosons have a radio emission, but we don't claim them as clear counterparts, because these here are the wise images, the color is the wise band, but the contours are Rax low frequency, that is at 888 megahertz. So we see that the wise boson does not match really the radio counterpart. So we cannot claim that they are radio counterparts of the bosons. And we also found another 2 sources with hints of radio emission, but the noises are quite, the fields are quite noisy. So we really need deeper observation of these sources to try to find a real radio counterpart. And this is what we did, because we asked for VLA observations. The very large array is an array of 27 radio antennas. It is observing from frequencies from 200 megahertz to 50 gigahertz at the resolutions are quite good from 0.2 up to 0.04 arc second. We can use these observations both for detecting gamma ray binaries or radio bosons. And we ask for, well, we submit a proposal in the semester of 2024A that just ended some days ago, and we end up with 8 boson or Babel-like candidates observed with BLA at this frequency band, that is the 13 centimeter band. So now this was all the work we did, and what are now our future plans? Well, we already looked for runaway stars in this sample of O and B type stars. We found for as a future plan, one possibility is to include radial velocities to this sample of runaways, and then we could find more runaways in this sample. But what can we do to search now for the binaries? So we are now looking for photometry variations in photometry or in radial velocity to try to find some binaries in this sample, and to find or to try to find gamma ray binaries, we need to continue this multi-wavelength search. We now have BLA observations, and we also need to look into radio catalogs of try to look for non-thermal emission in radio X or gamma ray catalogs. And once we combine all this information, we may end up with a list of potential gamma ray binary candidates. And for this, we want to also prepare observations of specific targets. But if we are looking for gamma ray binaries, we have to mention CTA, because to unveil the gamma ray nature of these binaries, we need to serve in very high energy gamma rays. So CTA will be an improvement as if we compare to the existing Cherenkov telescope, because we will have an improved sensitivity and a larger field of view. So for the sensitivity, CTA will be a 1 order of magnitude less, will improve 1 order of magnitude in sensitivity with the existing instruments. And this means that we will be able to see intrinsically fainter sources and more distance. And for the field of view, the large size telescope of CTA will have 4.5 degrees of field of view. The medium size telescope will have 8 degrees, and the small size will have a field of view of about 9 to 10 degrees. If we compare that to MAGIC, it was only 3.5 degrees. So now we will be able to make a survey of the whole galactic plane that will be especially designed to look for variability. So basically, the gamma ray community is now very exciting because the future of gamma rays is pretty promising. And another good news, we want to share our data in open access to both the scientific and the non-scientific community. So we have a website in preparation, but yeah, it is still in preparation. The idea was very nice, but then you realize that it's quite a lot of work to do this. But in the meantime, you can access our catalogs at this year. You can query them. We have both the catalog of the O-type runaway stars and the catalog of the B-type runaway stars. So you can really use our runaway data for your science cases. So I have done an extensive review of runaway stars, stellar bosons, gamma ray binaries. I really mentioned different fields. So I will just end with some take-home messages. The first is that we published a paper of looking for runaway stars in Gaia DR3 data. We found 175 runaway stars, and half of them were new discoveries. This was published in this paper last November. And now, as for the boson part, we found 13 new stellar bosons or bubble, and we are also evaluating this radio emission of these sources. This is a work that we are just going to submit to ANA, and yep, we are going to submit it. As a take-home message, searching for massive stars massive runaway stars could lead us to discover new gamma ray binaries or stellar bosons. And the multi-wavelength and the binary searches of these runaways are key to unveil population of exotic systems such as gamma ray binaries. So thank you. I want to mention that I am very happy to be here at IIC. It's very special for me, so thanks for the opportunity.
All right. Thank you very much. Do we have any of them? Does anybody have any questions from in here? Yeah, go ahead.
Hi, Mar. Well, very nice work. I'm wondering, in this preliminary work that you are doing now on searching for the radio and X-ray emission, so you're only like cross-checking catalogs with searching just for binaries that are runaway stars that have also radio and X-rays, or are you also limiting, for example, the setting some constraints to the X-ray emission or so? Because what I'm wondering, gamma ray binaries, most of them, they also have like X-ray emission, but the X-ray emission is not like super bright, it's more or less moderate. Or so are you also setting constraints, or for the moment are you just like cross-checking catalogs?
A ver, sí. Sí. For the moment, we are just looking for counterparts because our sample is quite large, so it's a bit difficult to go one by one star. So we are generally looking for counterparts, but one idea will be that try to look more specifically, putting some constraints in the X-ray part and try to see what is there.
Another question. I think you had.
Hi, Mark. Thank you for the talk. I have a question regarding the cross-match that you do with Fermi for the gamma ray binaries. Because, as you know, Fermi has a very big BeSS, so a few degrees, depending on the energy. So I guess at any point in the galactic plane, you will have many Fermi sources that are compatible with this point. No? So how do you restrict the sources that you see in the same position as the runaway star?
Yes, Fermi has quite large ellipses of a few degrees could be. So basically, first we look for runaway stars that were inside these Fermi ellipses. And then we try to look if there were known gamma ray binaries or associated astrophysical sources that were emitting in gamma rays. So it's really non-straightforward because the counterparts that I saw, I think we have 7 counterparts for the runaways. 2 of them were gamma ray binaries, and some of them have a wide field, but there is no another astrophysical source, gamma ray source in this region. So it's true that having a runaway star inside a Fermi ellipse could mean nothing because it's very wide, this field, but at least there are no gamma ray sources in the area. So the thing is that we need to use all the spectrum information to try to go to somewhere.
Great. I see we have a couple questions online. Jesus, I think your hand was up first, so go ahead.
Thank you. Can you hear me?
Yep.
Okay, thank you, Mar. Very nice talk. I really enjoy it, and I hope that you publish the GOSC paper soon. So I have a couple of comments. The first one is that indeed I think you are doing the right thing for just trying to start with the proper motions, not with the radial velocities, because the radial velocity have 2 problems. The first one is that, of course, if they are binary, you have to do multiple epochs. But the other thing that you have in some of these objects is that they have strong winds. So you not only have to measure the radial velocity by measuring the lines, but you actually have to model to see how much wind in filling there is. So actually, I think that's we've been trying to do some of these things, and we found that it really takes a lot of work working with the radial velocities, because otherwise you get systematic uncertainties that are comparable to actually what you're trying to measure. The other thing is that I'm glad you're finding this about the dynamical ejection being the dominant one, because that's what we're finding as well. We're actually, what we're doing is we're looking at very young clusters, and what we're even, I mean, so young that you cannot have the binary scenario, so you can only have the dynamical ejection. And we're finding that once you look into Gaia really carefully, you see lots of ejected stars, more than expected, because some of them are actually at relatively low velocities of maybe just 10 or 20 kilometers per second, which you cannot see usually with these methods because they are not that different from the rest. But again, we're finding more dynamical ejections than had ever been before. And we even have an object, which is the Bermuda cluster, the ionizing cluster of the North American Nebula. And we were able to find 12 massive stars ejected just within the first few 100,000 years of the cluster. So indeed, I think that once we look more and more into this, we're going to find that the fraction of runaways is really high.
Thank you. For this first part, of course, that's why we need people of the massive star community, because massive stars are really difficult to work with, and having experts in this part is very beneficial. And the second part, well, there were a lot of things, but we can comment on that offline because it seems really interesting. Thank you.
Great. Thanks, Jesus. I think we also have another hand online. I believe it's Dietrich. So go ahead.
Yeah, thank you very much. First of all, this was a remarkably clear presentation, so congratulations on that. I have two questions, if I may. The first one concerns the difference between O and B stars. The O stars are more distant on average, so the error estimates must also be larger, and we may have less precise knowledge of the theoretical local velocity fields. Could that also explain part of the differences, or that's something you have taken into account? And the second question is, in your search for bow shocks and circumstellar bubbles, you seem to have repeated work that was done by Julia Bodensteiner for her master thesis a couple of years ago in WISE data. And have you compared the results?
For the this work, I really didn't know about this work of boson certificates, because I compare my sample with these samples of the EBOS catalog of boson candidates of Perry, and we also compare with this Kobolnicki work, large sample of bosons from 2016.
Julia used the Bright Star catalog and all nearly 4,000 O, B, and A stars therein.
Okay, so we need to check that.
Great, thanks.
And the first question was on the difference between O and B stars and the different uncertainties between O and B stars.
I really didn't get the information. What is?
Can you
repeat?
Should I repeat my question?
Yes.
Yeah. The O stars on average are more distant.
Mm-hmm.
So that means that the estimates of the proper motions may also be more uncertain. And at larger distances, our knowledge of the local standard of rest may also be less perfect. And so this could also explain part of the difference between the O and the B stars, that the O stars have a larger proper motions than the B stars.
Yeah, that's true, because also when we compare the two samples in distances, we found that the O-type stars were more distant, and they also have higher velocities, higher uncertainties. Now I forgot to include this in my backup, but we have a study in our paper, in the one of 2023. We have a study in the different uncertainties in the contribution of each of them. And I have to review that. I can send you an email because it was interesting to see how it really affects each source of uncertainty to the runaway determination. But it's definitely something to take into account when looking to the runaway percentages of the two stars. Thank you.
Thank you.
Thanks. Any other questions in the room? I can ask one more last one. About the distribution of the O star velocities versus the B star velocities. The B appeared quite a bit wider. I think you had 9 for one and 5 for the O. We understand why there is such a big difference between those?
We were also wondering that because it's quite a high difference, and we think that it is because, well, B-type stars have longer lifetime than O-type stars, so they can basically have more dissipation during their lifetime than the O-type.
Okay, great. Thanks. If there's no more questions in the room, then I think we can thank the speaker one more time. Mark, you're here until Friday, correct?
Yeah.
Yeah, so she's here until Friday. So if you would like to talk with her or have any other questions, find her before then, because then she's gone. So thanks.